So we're talking about potential and a complete circuit and elements in a circuit. Now we're going to talk a little bit more about looking at a physical element to what a little drawing might be to what our circuits class drawing will probably look like. So for this guy, we have a battery. He's something that can generate energy. He can usually get those coulombs jazzed back up. They go in one end. You come out the other end. They're at higher potential to do some sort of work. So all you chemical engineers out there, if you do any research into battery design or energy storage, that's a good place to tie this class in. This is just a power supply switch, so I'm going to turn him on, but he's not the switch closing the circuit yet. So I have my battery. Something flows through him. He'll go from, a coulomb goes through there from low potential through the battery to high potential. So in that negative terminal through here, chemical reactions going on, gives it some juice, back out in a higher potential level. Then we're going to flow through to this point, and I have a little switch. So I have a switch here that I'm going to close. Only when that switch is closed can then current flow to go through there. So you need to make sure you have nothing open in your circuit. Then current can flow, and we're flowing coulombs current through this direction. Remember, we're assuming positive coulombs going through is our current flow direction. And then we have something here. This is just a little LED that uses some of that energy. So we have an element. We're going in one end of it at a high potential. Each coulomb goes in with some potential, and it's coming out at a lower potential out the other end. So as he goes through this light, he's at a high potential, he comes out at a lower potential, and then he flows back through here to the other end of the battery, and it's a complete circuit. I'm slowly using up the chemical energy in here to make this light to go through here. And these elements, we're going to talk about solve for element 1, what is it doing? They're going to either be supplying energy like a battery, or absorbing energy like a light, or, I don't know, let's see. Stick a little motor on here. Little motor. Let's see if I can get the fan to work. I have the horrible, luck of putting chalk on these usually, and then they don't work. Or a little computer fan. And each one of these is sucking some of that energy out, and then it's going back through, and this chemical reaction is giving some energy back to it. So that's what a physical entity looks like. This is a little sketch if you're trying to figure out what's going on. But when we go to actually looking in our course, just the beginning, we're going to have mystery elements. And they'll usually have these boxes and maybe a number in them. So this is element 1. So he's a battery. He's going, as the coulombs go through, they're going from low potential to high potential. And you want to know what the element's doing. Energy is being supplied by that element to the coulomb. So he's a battery. He's supplying energy to that coulomb as he goes through there. Element 2 is something that goes from a high potential, high energy state to a lower potential because that energy is used to do something in him. So element 2 is going from high potential to low potential, and the energy is being absorbed or used by that element. So I'm going to put these in a little box and send them around if you want to play with them. So I'm going to turn my power on here. And I have just a power source. That's what this light is. Over here, I have a slide dimmer, which is our variable resistor. And then right now, I just have a little light on here, an LED. So variable resistor, so if our resistance is 0, we have no resistance to current flow. What that was in our drawing is that I just treat it like a wire. I open this guy all the way up. Our LED goes to our full brightness, no resistance to flow, everything's flowing, awesome. No potential voltage drop across there because everything can flow through current-wise. The other extreme is infinite resistance. Seems backwards intuitive. For infinite resistance, you're turning your slide dimmer down. Really, really high resistance, nothing wants to flow through there. And then for these types of switches, we're varying our resistance partway between. You can see he lights up a little, he lights up more. You can get them really, really bright. Resistance to 0. Resistance to infinity. This works with other items as well. Put a little motor on here. Motor has some minimum value to get it started, so he's not moving, he's not moving. There you go. He moves partway through. We've reduced the resistance enough current's gone through that it turns our motor. Then we can make it go faster. So I'll pass this around just for you to play with. I'd like you to get a little bit physical feel for what these things are. and talk about some resistors. So in the inside the front cover of your textbook is this handy guide to how to read resistors. And you don't really have a lab with this class at all. So these are practical things to start looking at that if you're trying to figure out something in a circuit, you can read the resistance just based on the number of bands and the color code on here. And they give an example of how to read it. And this is probably going to be way too small to see. I might be able to do it. All right. So if we look at this 100 ohm resistor, and he has color codes across him that are hard to see, but we'll go through them anyways. So he goes brown, black, brown, gold. So brown, black, brown, gold. It's supposed to be 100 ohms, but there's like a decoder ring. So he's a 4-band resistor. The first digit, a second digit, a multiplier, and a tolerance percent. So if we look at our first digit, he was brown. And if you go to this little resistor color code here, brown stands for a 1 for a first digit. The second digit was black. That black stands for a 0 within this column here. The multiplier was the third band. The multiplier was brown. So if you go to brown, we look at the multiplier, it's times 10. So you take first digit, second digit, times your multiplier, 100 ohms. I put 5 different resistors on here, and their values are written here. If you want to try a different one as I'm passing it around, you can look at this 5.1 kiloohms. You should be able to do the band colors. If you guys are having issues with color, it's green, brown, red, gold. That gold goes to, the last one is your tolerance, and that's just, your tolerance for the number coming across there. So for example, it's supposed to be a 100 ohm resistor, so we have our meter. I'm going to pass this meter around too. If it gets turned for some reason, it should be pointing to the ohms as you're going around. There are 2 pointy things on here. Don't poke anyone with these, the adults. So we have our meter, we have ohms on here. It's overload because I'm not touching anything. Let's see, get it out of the glare. So for my 100 ohm, I'm just going to put it across here, across my 2 snap circuit contacts. Let's see what we get. We get like, come on, buddy. 102, 105. Go the other way with it too. Actually put it across its leads. 101.6. So it's not going to ever be exactly 100. There's going to be some variance in there, and that goes to that last number, and different ones are more accurate than others. This is supposed to be 1 kiloohm. So you have 1.017, 5.1 kiloohms, 5.113, and it switched here. You'll see to kiloohms for the units. 10 kiloohm, 10.17. 100, see 104.6. So I'm going to pass around this chart, these little guys, and this meter. I have 2 resistors. I have an R1 and an R2, and I have some batteries, and I'm going to go ahead and complete my circuit here. And we have our equations over here that we just derived. Now, we have a theoretical value, so let's see, this has a 3 volt written on it. In theory, these are 2 1.5 volt batteries in series that add up to 3 volts. Let's see, so that's our theoretical 3 volts to distribute. We have 2 guys in series here, a 1 kiloohm resistor and a 5.1 kiloohm resistor. So again, this is just theory, 5,100 ohms and 1,000 ohms, and this is R2. So if I plug those values in theory, my R2 will be, or my voltage drop across R2 will be 2.508 volts of the total 3 to use. So I got a meter. We're going to use them and see what we get. If you haven't used a voltmeter much, you'll see multiple items on here. This one with the little swirly guy is for AC. We're not using AC. We're using DC here. It's just batteries, and we'll talk more about AC and DC later in this course. But you'll see it goes up to volts DC. So if you're using batteries, you usually want this on DC to do your readings. And we're going to do some readings. So in theory, what did we calculate? Our voltage drop across R2 would be 2.508 volts. So this is R2. Let's see what we have here. I have 2.622 volts, so we're close. 2.622 volts. 2.622 volts. There could be a couple reasons why it's not exactly that 2.508. The first is this is magically 3 volts. All right, so batteries aren't exactly 1.5 volts. These are not made very, very accurately. They're made very quickly in mass distribution. So if we look at our batteries, we actually have, back on here, how much do we have to use? We have 3.145 volts to use to distribute. So this was 3.145. And our resistance values might not actually be just these theoretical whole number values. So we'll turn this guy to ohms and see what we get here. So on the 1 kilo ohm, we really have, oh, I'm messing it up, power going across there. 1.017 kilo ohms. And R2, get under there, buddy. Let's see, 5.113 kilo ohms. So again, there's no lab in this class, but as you go through, I'm going to try to show a few things that, okay, this is our theory, it's beautiful. We'll get 2.508. It really measured 2.622 when you're doing something in practice later on as an engineer, and there's all these potential spots where there could be that difference with it. So DC motor, I brought a couple for you guys here. This one, I covered up the board because I'm not actually using a program, the SparkFun program, but this guy was already stuck down, so pay no attention to the stuff under the paper. I just got a battery, and it has a little circuit to bring it up to 5 volts that it's delivering out. It goes out to 2 wires. I put my potentiometer in the middle so we can control the speed by just reducing that 5 volts down to some proportion that then just goes out to our little DC motor here. So I'm going to plug them in. As I pass this around, you can just pull one of the wires out and plug it back in, or you can just leave it plugged in and pass it to your neighbor. Either way is fine. When you plug it in, nothing happens because this potentiometer is turned where it's not sending enough voltage to get this guy going. So you're just going to vary this. I think we turn him clockwise. No, let's try counterclockwise. Counterclockwise. Come on, buddy. Uh-oh. He's not going at all now. Oh, my other wire's out. That would make a difference. All right, always check your wires. There we go. I don't know if you can hear it. Hold it to the mic. But it's spinning. And there's just a little gear end on there. You can slow it down, turn the potentiometer to it just getting started, and then speed it up a little bit. So I'm going to pass this around, just rotate this blue guy counterclockwise to send enough voltage to him to get him going. So little DC motor, you can see he's spinning really fast. This one's smaller, he doesn't go as fast, but he's also a DC motor. For this guy, all you gotta do is turn the power on to him. He's rotating, but it has the polarity switch in here, so you can change direction by switching the polarity. Turn it off, switch the polarity, turn it back on, and he'll go the other way. It's just a little switch here that you move up and down, but if you do it mid-rotation, you might end up hurting this guy, but it's okay. Life goes on. So these are DC continuous motors, things for you to learn something about as engineers, and the info's on here too. So the servo motor looks a little different. So it looks like a little black box. You can do a lot of black box analysis in your different courses. But it is a black box with a drive shaft and 3 wires that come out of this guy. So you'll see, here's our servo motor. He's got 3 wires that come out. One is for the power supply, one is for the ground, and then one is for the shaft positioning control that's sending that pulse width modulation to tell it. Inside of here, there's actually another little motor that's geared down to do this very, very slow control. So it has a little feedback device in this box. There's a lot packed into this little guy. That's why it takes some size to him. And again, you need something to tell it the pulse width modulation. So in this case, I do have the board hooked up. There was a program in that kit that talks to a servo motor, and this is the kit next semester that all the students will have. But if you want to rotate something to a specific position, and there's a little program that goes and tells it what to do. On this one, just plug in the 9-volt battery, and I'll just pass it around plugged in, but it might freak you out that it's always moving on you. See what he does here. So you can rotate, hold a specific position, move very slowly, and you can program it to do a specific slow amount of rotational pattern with a servo motor. So actually I'm gonna, if you want to unplug the power in this one, just pull this guy out here. Another version of a servo here. This one, the little program, the pulse width modulation, is also built into this chip. So on this one, you just turn the power on, and it just does a simple oscillating back and forth between positions. But hold these, feel it. It feels different than the other motors. You can feel that there's a little gearbox inside of there as it's rotating. There's something going on in this mystery black box, but this box is necessary to hold those other things. And these, you'll see, have 3 wires coming out of them. And that's how you can tell their servo has the additional wire. It's only rotating less than 180 degrees to a specific position. So yeah, you're not going to break either one of these. I'll pass this one around plugged in. Just have fun with them. But holding onto the box, you can feel a little bit of what's going on in there. Maybe I should, we'll find a way to pass them around plugged in. There we go. All right, cool. Thanks, guys. So first we'll start on this side. Cover up the side over here. These are some different capacitors. These 2 are ceramic based. And then these 2 down here, and the one I'm going to use in the demo, are electrolytic capacitors. The design of them and the fluid that's in them allows you to get larger capacitance in a smaller area, so you can get 10 microfarads, 100 microfarads in that little volume. You've probably seen these in different devices, just how they're designed. And then this guy's a variable capacitor that you can turn the little knob on him. You can kind of see into that window. I'll pass it around for those of you in class. That it moves some plates in there about how much they're overlapping to have those 2 plates standing off from each other. And this is for very, very small capacitances. It goes to, 4 times 10 to the minus 5 microfarads, or to 2 times 10 to the minus 3 microfarads. So very small numbers of capacitance, but you can vary it, and this is used for high-frequency radio work. So when I pass this around, you can see some of these different capacitors. You might have seen them in different devices you've broken or taken apart or tried to fix. But for how a capacitor really works is I have a circuit here. I have a battery stack. I can choose to connect my battery to my capacitor, my battery to an LED light, or the capacitor to the LED light just by clipping on my wire on some things. Right now my capacitor doesn't have any energy in it, I don't think, because when I connect them to the light, nothing's happening. But if I connected my light straight to the battery, he lights up. You know, I have my current path going through this portion of it and lighting up the LED. If I take my discharge capacitor and connect him to the batteries for a little while, I can build up a charge in him. He has this little spiral of, I think it's paper in there, separated by oil, or paper in the oil is the dielectric, and there's some sort of metal coil in there that it's held across, and you're building up capacitance in him. And when he has enough charge, I can disconnect it from the battery, so battery is completely out of the circuit. I'm going to try to use it to light up my light bulb now. So if I connect it to the light, you can see it gets light and then it discharges. Let me do that one more time. Charge up my capacitor, and then light up and fade away. So I can charge this guy up, store energy in him, and then he's used for something, and you can see what that discharge is like. Not a whole lot of energy, but enough for some things. Or you can stack these in an intelligent method to get a lot of them. So I will pass this demo around that you guys can play with it. Try to charge up your capacitor, discharge your light, and you can look at some of these different other capacitors in here. The importance of this is if you're trying to design something to hold a certain capacity to use the energy later, if you design your circuit with them in parallel, you're actually building up more capacitance to then be able to use to light up your light bulb or do something with that energy. Realize they're different than resistors. We'll do some problems, not today, where you have your drawing of capacitors and some little geometric configuration. You have to decide if they're series or parallel and reduce them down to see your total capacitance. But I want to talk about capacitors in parallel and how can they function. I have a little visual demo underneath the overhead here that's some capacitors that are hooked up in parallel. So right now, this switch is off, and this is a 470 microfarad capacitor, so he's not in the circuit. What is in the circuit is this 100 microfarad capacitor, an LED, and some batteries. If I press this switch, I'm storing energy in that capacitor, which can go to the light bulb. This guy is off. He's out of the circuit right now. So we're going to block him off. I'm going to pretend he's not here because I need to put my hand around this light. So right now we're just going to use the 100 microfarad capacitor. I'm going to press the switch. He's powered. He's powered. When I let go of the switch, you'll notice it does not instantaneously shut off, but the energy that I've stored in the capacitor is then used, and it slowly discharges it, and you'll see the light slowly go off. So see it discharges off. So lit up, slowly discharge off. If I take the capacitor out of the circuit, on, off, just shuts off. With that capacitor, you have a discharging effect because it had stored up some energy in there, and then it slowly fades off. But these two guys are in parallel. I'm going to turn this switch on. So these are both now parallel capacitors. Parallel, you straight add. So 470 microfarads plus 100 microfarads. We're going to have more energy stored in the electric fields inside these little capacitors to use for the light bulb. So if I turn the switch, while they're discharging, it should last longer than it did when just the 100 microfarad one was there. So he's lit up. He's lit up. If I unlight the switch, and then I'm going to unclick the switch, I'm going to use the energy then from the capacitors. You see it takes a little while longer, actually quite a bit while longer, for the light to completely go out because we've added a big fat 470 microfarad capacitor in there. We light them up, light them up. Now it takes a while for that light to go off. If I switch off that, here, I'll light them up all the way. Light them up, light them up, light them up. If I switch off that 470 microfarad capacitor, it'll much more quickly fade away. I'll pass this around, you can play with it, but capacitors in parallel, if you're stacking up that energy in electric fields to use later on in devices when you're designing things for engineers, you want to stack them in parallel to get that added effect of them. We've talked a lot about resistors, and this is going back to resistors, but I want you to know about some of the different types. So this little guy here, he's patterned, is called a flex sensor. And he's a carbon pattern on a piece of plastic that's very flexible. They'll say flex sensor, you can bend him. And the reason they do this is as you bend it, you're spreading out or getting closer together the electrically conductive items on here. And as you do that, it changes the resistance. So this is something that can be built into like a glove or something where you're controlling resistance signals to something through physical motions, or in an automated process if you're setting up an assembly line or in transportation if you have flexible sensors embedded in items that trigger it as they go by. We're going to show another example of a voltage divider. For all your majors, this comes into play a little more, and that something is becoming a control for a signal. In this case, it's a flex sensor, so you can embed this in any type of engineering device. We're sending voltage to it. By how much you flex it, it varies the resistance. It sends a reduced voltage into the little computer card. The computer card in here, then based on how much voltage is coming to it, sends out a signal to turn a little servo motor some set amount. So I'm going to plug them in, and I'll pass them around when we're done showing it. So again, we have our little servo motor. Remember, servo motors are good for turning small amounts under high torque, very controlled rotations, but only up to 180, some go to 210 degrees of rotation. So this flex sensor, when I pass it around, if you just bend it, it doesn't do much. You actually have to, like, if you just push it down, you actually have to bend it, like put a curve in it. Don't worry, you're not going to break it. So I'm going to put one finger underneath and my thumb on top. And you see as I bend it, I'm varying the resistance, which varies the voltage that the little computer program then says to the servo, if you receive this much voltage, rotate this many degrees. If it goes back down to so much, rotate back. So it's a simple device, but these are some of the basic circuit concepts: a voltage divider, different types of variable resistors are actually sensors you might buy within your majors. And again, servo motor, when you're holding on to it, feel it. We talked about how it has gears in this little black box. There's a lot of controls inside this little shape, and you can feel them doing their work if you hold on to the body of it as you're flexing the other thing. So again, flex sensor, carbon on plastic, acts like a variable resistor. The more you bend it, the higher resistance. This particular one goes from 10 kiloohms to 35 kiloohms as you're bending it. When you bend it, it's a voltage divider. That voltage is an analog signal. Remember, analog's a range of voltage. It goes as an input into the computer program, which turns an output back to our little servo motor to rotate it. Some of the majors in here: material science, chemical. These flex sensors are very much designed by material scientists and chemical engineers for the components in them. You might need to make different ones for different applications, electronic materials. MAE and arrows, servo motors and controls. You're going to get to control lab. You're going to be controlling all kinds of things using switches and signals and a computer program back to motors when you get to controls lab or control anything you're building. Nuclear, this goes back to that thing of maybe building it in a glove and manual dexterity. These can be used a lot in remote applications for nuclear if you need to control a robot, control other things by using your hands in one spot and something else is actuating somewhere else in a nuclear environment. ISC in the civils, lots of different sensors for your process control if you're setting up an assembly line, packaging. Within civil, these are embedded in construction and other items for having something trigger some sort of motion based on how much force or flexibility is going into it. So I'll pass this around, play with it. You won't break it, so don't worry too much about it. So we're going down to less coils. Again, primaries the powered side, secondaries what we're inducing it in. Transformer signal, coils, little gap in between. Again, the way a transformer works is you have to have an AC source. It has to be this alternating source to induce a magnetic field in the coil. Just a straight DC won't do it. It's just sitting there. You have to have this repetitive pattern on the coil to induce a magnetic field, to store that energy in a magnetic field, almost like an inductor, and then shoot it across the gap because of that repetitive signal. And this could be a sinusoidal wave, it could be a square wave. It's just got to be some sort of pattern that's not a constant held DC. So this guy could be a sinusoidal wave, it could be a square wave, some sort of AC power source that's alternating in a pattern. DC, you're holding out some straight line of voltage. It's not going to work to pattern it to power that coil to induce a magnetic field in the other one to induce a voltage difference that'll have current flow and do something down the line from there. So I brought a little tiny AC demo. And in transformers, again, we talked about it being an AC source. So I have here batteries, which are DC, a switch, a transformer, a regular light. This little side on its own, I can power it, and my light is on. Power's going from the batteries through the switch, through this side of the coil, through the light. You'll see this other side with the LED isn't on, the side that's on the other side of the transformer. And we have our DC power source, and he's a constant current. We're not powering the other side. Now, there's a way to fool a circuit. So you can induce AC using a DC source by kind of simulating a square wave. So if I hit the switch on and off and on and off and on and off, it's like making a little square wave or little spikes in the power. So it's a repetitive source. So I'm going to fake this thing out, making the batteries, the DC source, look like AC by just switching the switch really fast. And if I do so, I'm going to charge up this coil, my primary coil, to induce a magnetic field in the secondary coil, which should then allow current to flow this way. So again, if I just turn it on, nothing happens. But if I switch it and kind of fake it out and induce an AC source, I don't know if you can see that little light lighting up. Try to get them out of the glare. You can get this light on the other side to light up, and you can also see the meter over here is registering something. But if I just hold it steady, it goes to 0 and it doesn't light up. So that's the cool part of this transformer, is this guy has no power. There's nothing going to this other side. There's a gap in between here, just two little coils at a standoff for each other, that you can induce the magnetic field on the other side. And then I can simulate AC with DC by just switching it. So I'm going to pass this guy around for you guys to play with a little bit. So one thing that you guys asked about was piezoelectrics. And there's this little piezoelectric buzzer. Piezoelectrics, I'm going to do my little thing. Piezoelectrics are material that have the ability to, if they're put under strain, if you flex them, you put them under pressure, the word came from pressure, the origin of piezoelectric, they will induce a magnetic or electric charge based on the crystal orientation. So some questions were about piezoelectrics. And this goes both ways. So it's ability of certain materials to generate electric charge in response to stress. But it's also reversible, that if you give them, send an electric charge, you can make these materials, you don't induce stress, you induce the physical aspect of strain, which you remember is like a change in length over length, up to about 0.1% strain. And these are crystals or crystalline materials for you materials engineers. They're also in the body, so bones are piezoelectric materials, so they can, under certain electric charges, if you have stress in them, send out an electric field. I'm trying to see some of the other interesting things that were about this. DNA is, there's certain ceramics, but the ones in more practice of devices you might see are usually the crystalline materials. The beginnings of this were sonar in World War I. So they put some quartz crystals on a device, and they were able to use sonar to bounce signals off and read it back, and the small changes in timing of that bounce back and the stress induced from there, they could tell the distance to something. So this was one of the beginning applications of that. From there into There's a whole lot of different ones. There's ones for distance. I'm going to talk about the ones for sound today. So this one is a piezoelectric buzzer we have under here. So, and this is part of this little kit, is a piezoelectric buzzer. And what it does is, I need a pen. You have two plates, essentially, of materials on top of each other, and you do an induced different polarity on them. But because they have that crystalline material in them, they want to bend one way or bend the other, and you can change the frequency of how those disks are fluctuating to different hertz. And when you change that fluctuation of disks, they push air out, and that becomes sound waves. So that's about the beginnings if you want to talk about speakers and sounds, but this is an electrical application of that. So the kit comes with, this buzzer, and it makes one sound. And Chelsea was sitting in office hours just working in there, and a student I was helping, Sarah, she's one of your peers in your class, was like, "What are you doing?" And Chelsea was trying to figure out notes to do Mary Had a Little Lamb. And she's like, "Okay, let's look at this. Well, your peer student, Sarah, played piano for many, many years." She's like, "Let's do something better." So she left my table, which I was helping her with problems, and she totally said, I got to go see this. So she went over and hung out with Chelsea, who's your TA just working on these. And together they learned about the different hertz and the different frequencies that indicate notes. And they wrote a slightly different song for you guys than Mary Had a Little Lamb. And I'm going to take my mic off and put it up to here when I plug it in so you can hear the sound. So I thought, that was awesome. They went off and they did their thing. So these are two students. One is your student in your class now. One is someone who had just recently taken the class, very little knowledge, decided to learn about piezoelectrics and hertz and sounds and notes and put that together. So if you are into thinking about Arduinos, I really encourage you to tinker some. If you're intimidated in getting started on your own, find a kit. I like this one because it's really, really well documented. It goes back to what is an electrochemical cell and what is current flow. And for you chemical engineers and material scientists, it doesn't have to be these magical chemicals you get in a lab and put somewhere. What's happening is an exchange of an electrons, which we learn in circuits as a movement of current in the opposite direction. But all you need for that is an anode and a cathode. So if you have an anode, I'm going to probably do this up here. That's why I even opened this screen in the first place. An anode is negatively charged. A common material to use for this in this type of demo is zinc. A cathode is the positively charged one. A common one is copper to use for that. And then if you put these two items some distance apart from each other in an acidic environment and make a complete circuit, they want to exchange electrons. So we'll show some of these guys. So say you have a stick of copper and a stick of zinc. We'll make this guy zinc. He's negatively charged. Make this guy copper. And he's positively charged. And for the one that we're going to do as a demo, you don't get enough unless you have two in series. So to connect them in series, we'll set up another little cell over here. And this is all a cell is. A cell is like a battery. All you need are two things that are going to exchange these electrons in an acidic environment. So we'll do another zinc stick and another copper stick. And to connect them in series, we're going to do the positive one to the negative of the other. And then to connect it to some sort of load, we take one end of this, connect it to our load, whatever you're going to power with your little battery cells here, your two battery cells in series. And then to connect them in series, we're going to do the positive one to the negative of the other. And then to connect them in series, we're going to do the positive one to the negative of the other. And then to connect them in series, we're going to do the negative of the other. And then to connect them in series, we're going to do the positive one to the negative of the other. And then to connect them in series, we're going to do the positive one to the negative of the other. And then to connect them in series, we're going to do the positive one to the negative of the other. And then to connect them in series, we're going to do the positive one to the negative of the other. And then to connect them in series, we're going to do the positive one to the negative of the other. And then to connect them in series, we're going to do the positive one to the negative of the other. And then to connect them in series, we're going to do the positive one to the negative of the other. And then to connect them in series, we're going to do the positive one to the negative of the other. And then to connect them in series, we're going to do the positive one to the negative of the other. And then to connect them in series, we're and connect this back. Now, I'm going to switch colors for clarity here. So each one of these has to sit in some sort of acidic environment for the exchange of electrons to happen here. So now this is some sort of acidic environment the anode and cathode are living in to make up our little battery cells. And for the flow of what goes on, well, we'll switch colors one more time. I apologize to the colorblind folks out there. Current goes from positive to negative, so I'm going to draw the green line for our current flow direction, and then our current would be flowing through our wire. That goes to whatever load thing we're going to do. Current, current, current. Again, positive to negative across there, current, and he's flowing through. Now, we do all these equations and circuits, and they're derived with this beautiful theory of current flowing, but we know actually the electrons are moving. So what's really happening physically is, we'll make electrons blue, is electrons are going the other way, or opposing current, all the way around. But all you need are an anode, a cathode, a negatively charged material, a positively charged material that want to exchange electrons, and in order for them to do it, one, they got to be in an acidic environment, and two, there's got to be a complete path to go around, and in this case, we're gonna power a little clock here with our two cells in series. So you need two in series with this kind of environment for it to work. And first I'm going to show the demo, but then I'm going to talk about it. There are groups actually doing scientific research on it. It is a fun science project, but there is actually other things that are going on with it that we'll talk about. So I'm going to go to the overhead here, and I'm going to put some cells. So we have two acidic, slightly acidic cells here. And I have a little clock. And I have some things that are anodes and cathodes, assuming I can unstick them from each other. So for this, make sure my direction right here. I'm going to stick a zinc plate, you can see the color difference, in one potato, and a copper plate in the other potato. And these two aren't really hanging out with each other. They're just making the path between one and the other. They need an opposing pair, hopefully some parallel distance off of it. They said about 2 centimeters works well. So we'll see if I can get this thing to work. So I'm going to take a copper one to go with my zinc one, so I have an anode-cathode pair. Try to make them parallel. Stick them in the potato. And then let's see if I can magically make this work or not. I'll take my zinc one to pair with this copper one. Da-da-da-da. Ha-ha. We have our potato clock. And then we're going to do like some sort of scientific thing with this. So I'm going to turn on my voltmeter, and let's see. Cool thing about this voltmeter is the screen comes off, so I can just put the screen up here for you to see. All right, so I have my voltmeter, and let's see what we're getting out of these two taters here. Oh, I have it stuck negative, so stop rolling, dude. There we go. Negative 1.5-ish volts, because I have them flipped. Got to get my anode cathode right here. Do it properly. Should be, yeah, about 1.5 volts. You can see that floating number out of two potatoes in series. And it can be any acidic environment, so I wonder if more acidic works better. So I got a lime that we've cut in half here. We'll try our lime one too. Again, the same thing. We're going to put these guys, there's an anode and a cathode, the middle connection. All right. The one that has zinc needs copper. You need to have a pair. closer there. And then the one that has copper needs zinc. Wait, we have to do the reveal. Get in there, clock. Wait. I'm conductive, so it was working with me. All right, there we go. So we have this other little clock that works with a lime. Let's see what we get out of the lime here. So we have an acidic environment, anode cathode pairs. We have 2 limes in series. I don't know what we get out of this. Oh, I touched the right spots. About 1.8 volts. There's different things too. I have these pushed in different depths. There's different areas of electron exchange. And if I brought 2 limes, probably would have had a larger value. My lime clock's going, blinking. Why are you blinking, buddy? There we go. So this is kind of fun. It's a neat trick to see how it works. It's good to understand the chemistry of why it works. And the reason as engineers, as one chemical engineers, you should know how cells work. Everyone should really know how a basic battery works. But the other aspect is there's opportunity to make some difference in this area, which seems weird. How can I make a difference in potato circuits? And the way is there's a group, and I'll email this link out because for some reason Canvas isn't letting me edit the syllabus today. There's a group at the Hebrew University that is actually taking potatoes, and they found a way to optimize it to get more than 1.5 volts, many, many more orders of magnitude more, by they boil them for a certain amount of time, and they put them in a different configuration. And they found that they can reduce the cost of batteries, like a D-cell battery, about 50 times less cost to power. And this could be applicable in different areas. One is in countries where power is not really accessible. There could be food. You could use it for that. Unfortunately, those countries usually also need the food for food. So there's another aspect is that we throw away a bunch of food here. Like, people throw away way too much food. So people are looking at research, and if you are into environmental field or sustainable applications of your engineering major, thinking about taking food waste and taking material waste, there's waste copper, there's waste zinc, and making power sources out of waste is a really, really cool research area if you get into it for a better existence of us as human beings. And then there's even a third level. As an owner of, I have 7 chickens in my backyard. As an owner of chickens, even something like this, say you power your potato battery for a number of days, chickens can totally eat that after like a few days once you're out of cells of that. So there's like a third point. If you're using food waste, maybe get some energy out of it, and then I throw it at chickens, and they give me back eggs, and it's a really, really good exchange we have in our yard. So I will email out some of these articles, but it's trying to think of electrical applications of some of your majors that might be something one-off that can do really good things for for society as a whole, for third world countries, but also just thinking if you are looking at some sort of self-sustaining setup or off-grid setup, think about food, and waste food is another source for some other things that are going on.